I'll have to wait for the next highlight. So the announcement is that a bunch of stuff in my bag. Right. Guitar picks, Canadian monies, old AirPods, clipper, and all the shit that I'd really need to have in my backpack, clearly. So I have an unexpected medical situation in the family, nothing too serious, but as a result, so basically my wife needs to have a medical procedure next week, and we have to travel for it. So next week is going to be a Zoom week. So both the Monday and the Wednesday lectures next week will be held over Zoom. Again, I wasn't planning on it, but it just so happens that Monday and Wednesday I will not be able to make it to campus. I don't really anticipate it being a problem. If any of you guys object, like if any of you guys feel, like you really, really hate having a Zoom week, just let me know. And, I'm willing to listen to your feedback. But I think for this course, basically anything like software centric works really well. And I'll do my best, just like last time we did the SVD example. I'm going to do something like that, I think, for both days where we step through some analysis, and I'll try to do something in Python for at least one of the days. Okay. So I will share my screen and I will actually resume what we were doing last class, which is I'm going to finish up the minimization. And so I think what I'll do first is, there we go. I'll just to reorient everyone as to what we were covering. I just wanted, the goal of this little interlude was just to, so when you see optimization in machine learning, which there's a lot of, that you're not completely in the dark. No, not preface, interlude. They're not completely in the dark as to what is going on. And so, by the way, in terms of like, not much has happened in terms of in the optimization world. Basically, the state of the art hasn't changed a lot in decades. And where things are is, give me just a second to figure this out. Where things are is if your function is convex, we know how to, like we know that we have the tools to solve it. We have very good numerous packages to solve them. If your function is not convex, we still do gradient descent. In other words, there's no new ideas really, other than to just like, if your function is not a bowl, oh, I know what's going. If your function is not a bowl, then, oh, all right. If your function is not, so this is the function here, cursor, W transpose W is a bowl. It's quadratic, it's a convex function, it has one minimum, and now one minimum, so that one local minimum is the global minimum. If your function is not like that, which is the case for all deep learning minimizes cost functions that are not convex, meaning that they have many local minima. And believe it or not, the same tools are used to minimize those as are used to minimize convex functions, except that people just run the search many times from different starting points, essentially. But it's still just gradient descent. And so what I wanted to say is that nothing much has changed. That's maybe too strong. There hasn't been a revolution in the way that optimization is done. So these techniques that I'm presenting here with the Lagrange multipliers, they're still very relevant to what is actually done in modern day machine learning.
You're sharing it like the presentation kind of?
Yeah, that's what I want for the. Oh. No, yeah, I don't.
We see your screen. We don't see what you're sharing on.
Yeah, yeah. You know what? It may actually be. It may actually. Am I mirroring? Oh, I am mirroring. Hold on. Mirror displays.
Yes, now we can see much
Now
better.
you guys can see. Okay. Thank you. You guys see it?
It's so weird.
It's still weird. All right. All right. Yeah. What if yeah, it's because PowerPoint's like
You're showing it as a show. If you just like.
what about this? This fine? Or no?
Yeah,
I mean I don't
know it doesn't work. It should just be.
so if I do show, right? It won't you guys still see the whole thing?
Yeah, see notes.
We see the notes.
Okay. Oh,
I mean, it doesn't matter, but before even this, we were seeing like small different things from your screen, which was in the way.
I need to be able to hear her. So I need my speaker on.
I wasn't sure she was talking now.
Yeah, she is. Yeah, she's talking to me. Yeah. She yeah, no, I know.
Actually, I'll stop talking because you
No,
guys
no, no,
are.
no, it's no, no. No, stop talking. It's all good. Look, listen, I'm actually just putting up the slide to refresh your memory that this is this is called the Lagrangian, and it's a combination of the thing that you're trying to minimize, which is a quadratic, plus your constraint multiplied by this lambda, which is called the Lagrange multiplier. And the technique is to basically differentiate L, the Lagrangian, with respect to W and minimize and set that to 0, and minimize the Lagrangian with respect to lambda and set it to 0. And what we saw, maybe see if I can new slide, see if I can do this in real time. New slide. What we saw basically is that the optimal, it's different because I'm in, you're killing me, PowerPoint. Everything but what I need. What we saw was this equation, if you remember. Fraction. This is in the denominator. It's not going to let me delete just that. Oh, well, okay. Right, this was the solution. And I'm giving you this because we're going to implement it in just a second in MATLAB. Right, so this is the theoretical solution, which I solved on the board last time. And you know, again, you should convince yourself by actually solving these two equations simultaneously that it does indeed bring you to this. So now let's go and show this in MATLAB. So I will, let's see, this was, okay. Oops. Starting here. So I'm going to set up my problem. So the D here is a dimensionality of the problem, which needs to be 2 for me to show it to you geometrically. The A matrix, that's our like, you know, that's the equivalent of the coefficient multiplying the x squared term in the standard quadratic. It's a matrix. Remember I said it basically has to be symmetric, which means that the transpose of the matrix is the same. So this is A and this is A transpose and it's the same. If it's not symmetric, another definition of it is if you look at the eigenvalues of this matrix, they're both going to be positive. But let's create just a random matrix, a random 2x2 matrix. If you take the eigenvalues of a random matrix, and if one of them is negative, then this will not work because the basically what it's going to mean, what is it going to mean? It's going to mean that our definition of the gradient of a quadratic, which I'll just write in the comments here, gradient of W transpose A times is equal to 2 times A times W. And that equation presupposes that A is symmetric. If it's not symmetric, it's actually equal to it's actually equal to A plus A transpose that. And when these two are equal, you get the familiar expression, which is here. Okay. Okay, so we have our A matrix. I made it symmetric on purpose. Then I'm going to take, and this is going to be, oh, this is unconstrained. Sorry, I'm jumping the gun. I meant to go here. Yeah, that's there's no B here. I'm just I'm neglecting the linear term because it doesn't matter. I don't need the linear term to make this a quadratic. So here's my function handle, which evaluates my quadratic for two-dimensional weight vectors W. Here's my constraint vector D, right? So we need our solution needs to satisfy D1 times W1 plus D2 times W2 is equal to 1. Remember, if you remember from last class. So the coefficients of the hyperplane D can just be random. It doesn't matter what they are. So I'm just going to randomize them here. And then I'm programming in my fmin_con function. So I'm telling MATLAB to minimize, to perform a constraint minimization of this quadratic. 0, 0 is just the starting point of our search. This could be anything. I can make this. Another option, by the way, is just to make these small positive numbers. This empty argument just means that there's no inequality constraints. These two, this is an inequality matrix and this is an inequality vector. And here's the core, here's the input, the argument to tell MATLAB what our constraint is, right? So this just means that D transpose multiplied by W has to equal to 1. And then we're going to compute we did this last class, I believe. We're going to compute our theoretical solution and we're going to compare it to what fmin_con generates. And so that the first column here is a W star from fmin_con, and the second column here, right? So if this is W star and this is W star theory. And the theory is that equation that I wrote on the PowerPoint just before getting into here. And so they're the same, which is a good sign. And now the part that I tried to do right at the end of class, I'm going to demonstrate it for you now. So what I'm going to do is render our cost function, our quadratic, on a two-dimensional grid. And the grid in both, so the two dimensions here are W1 and W2. So W1 is the first classifier weight and W2 is the second classifier weight. And so you have to kind of wrap your head around treating, evaluating everything with matrix operations. And so when I evaluated this line number 52, and I see that W1 is 100 by 100 matrix. And if I plot it, I think you'll see, right? So it's just the values of W1 and they're in, so this is the two-dimensional plane And you see that W1 is increasing as we go from left to right, which is exactly what we want, from -5 to 5. And if I do the same thing, for W2, you see that sure enough, it's increasing. And probably what I'll do is I'll just put this in the code so that it's permanent. So that you see what the grid looks like. And next thing I'm going to do, and this is the step that I was blanking out on last time under pressure. Right. So our equation is, well, you kind of see it here. So our math equation is that there's the two terms that have the same W squared, and then there's this is our math equation, a quadratic. And now I'm going to implement it as a matrix operation. So to do that, notice that what I need to do here is at every grid point, I take the value of the W1 dimension and I multiply it by itself. So this is a multiplication of a matrix by a matrix. So at every element, the two matrix elements are getting multiplied together, right? This is important because this is not a regular matrix multiplication. This is an element-wise multiplication. So if I look at one way to see this, if I go W1 times W1, I see this. So I'll actually, right? So this is W1 times W1, and this is W1 element-wise times W1. See, they're very different. And the one I'm looking for here is the element-wise one. Right? These are basically, I think these are going to be zeros mostly. Yeah, very small numbers here. So this is the one that I want, right? The square gets larger as you move away from 0. 0 here is at the 50, at element 50. And then I do the same thing for the other three terms in the function, right? So I multiply W1 element-wise by W2, and then multiply that by the scalar A12, and so forth. And now F2 is going to have the same size as my grid. That's the key. So F2 is just a function over my grid. So the grid has two, every element of the grid has a W1 value and a W2 value. What I'm doing here is I'm transforming those values into the function, into my quadratic. Okay, and so now the moment of truth, I will put this, organize my code here. I'll put all the, oh wait, what did I just do? There we go. This is, okay, so I'm going to unpack this statement a little bit. I just want to put everything else here. Okay. So contour is a function, well, as you can guess, it makes a contour plot in MATLAB, and it needs three inputs. First input is your grid of X values, second input is your grid of Y values, and the third input is the function that you're evaluating over that grid. And so these all have to be the same size matrices. 70 is the number of contours that I want to plot. So I'm going to go ahead and evaluate this. And first, we'll just verify that, sure enough, we have a contour plot, and the colors of the contour lines tell you the value of the function. And I was like, this is a quadratic bowl. And so as you get further away from the center, the value grows. And I'll show it to you as a surface plot also, or the, what's the cool one? The 3-dimensional one. I think it's called surf. Yeah. Now I'm gonna overlay our constraint over that, right? So our constraint, I've also defined a function here. I'll paste up above, put all my, okay, so this is the same logic as above, except that now I'm trying to render our constraint, which is d transpose W is equal to 1. So now what I'm gonna do is evaluate this. You know, maybe I'll make this on a separate figure actually, because I want you to see it clearly. Okay. Oh man, something. There you go. Too many figures. All right. I'm running again for a different. Running again. What I want to do is I want to try to convince you. Okay. I can't get the contour to. What I'm trying to do is get one of the contours to match exactly here, but I of course I had it upstairs 5 minutes ago, but not live. So what is this figure showing? First of all, the contours are obviously the objective function that we're looking to minimize. And maybe what I'll do is I'll make the constraint. Let me see if I can do this. Let me make this thicker. Yeah. So the black line is our constraint. And so what we're trying to do is find a point on the black line that has the smallest value on that bowl, right? And so if we were to take the center of that bowl, it's actually interesting. It doesn't look perpendicular, but let me see if I increase. It is the minimum, right? Because we confirmed it in 2 different ways. We confirmed it both with fmin con and with our analytical solution. Maybe if I do 200 contours, we'll see. Oh, that's pretty good, right? So here, actually, it is tangent. It is, right? So the result, the Lagrange multiplier result is basically that there's a special relationship between the contours of the function and your constraint, and the solution, the solution to the constraint minimization problem happens to lie basically at that point of intersection, you know, at that on the line tangent to the contour. So it's actually not, I still don't think it's perpendicular. It's interesting. It is tangent though.
Like if you increase the contour is gonna go to it.
Yeah, but what I'm saying, if I put down a point at the minimum of let's see. No, it does touch. No, that's true. But I'm saying it's not the origin is like here, right? And so if you draw a perpendicular line, it's not perpendicular. You have to go in the direction of the major axis of the ellipse.
Oh, that's what you're saying.
Right? Which is in.
If you want, you could add
Um,
Yeah, I just want to draw it.
yeah. Oh, yeah. That's a good. Yeah. So, right. It's a good idea. So, what I'm trying to say is, oh, actually, maybe use the line so that I don't. So if I take a point from the middle of this, the minimum, and I make a line that's it's not going to be perpendicular to the constraint, obviously, but it is. Oh, it's really interesting. So it's actually, you need, so I think you need both. You need both the major and the minor. It's actually a combination of the major and the minor axes, which is cool. But I think it's either on the, I think it's probably in the Wikipedia page that has a really cool demo that shows you this. It shows you this result, that that it's tangent to the contours. Anyhow, this is just geometry. The important thing is that we did, oops. The important thing is that we did confirm that the analytical solution from the Lagrange multipliers matches, a numerical solution. So like if you ever encounter a problem, in your experiments or in your future jobs where you need to solve a minimization problem, you would probably use something like fmin_con. Fmin_con is like super ubiquitous. And there's a Python version of it. It's called, I think it's called minimize, actually. It's in SciPy. So they're super useful because you can minimize any function. And here we just demonstrated that those functions minimize can sometimes have a closed form solution, right? So this is what's called the closed form solution, meaning that you can write the solution to your problem as an equation. In most problems, you cannot do that. Okay, what I will do now is proceed with the discussion on support vector machines. So this is a challenging lecture for me to give because hold on, why is this so blown up? Because it's so mathematical, and it's not like, okay, hopefully everyone can see this or will be able to see it. So the problem with teaching this is, and I will share a link. I thought about how to do this. Still no. My computer sees it. It's probably the $4,000 Mac can't handle all these things. Okay. We're done. We actually turn off MATLAB to save. My computer doesn't blow up. I like to keep my fingers open. I actually don't. All right. So my goal, my plan for tackling this is I'm gonna gloss over it basically, and I'm gonna if those of you that want like the nitty gritty, Andrew Ng does a pretty good job of teaching this in one of the online, Stanford released their machine learning course on a CC BY license, so anyone can use it, share it. So if you want to know the mathematical details of this, it's in the slides, but they're also, Andrew Ng does a pretty good job of explaining this. The problem is that support vector machines were invented by a dude working on mathematical equations. So I cannot think of a way to teach it without mentioning the math, unfortunately. And so what we saw last class is that the we're looking for the W that maximizes the margin. So we're looking for the hyperplane such that separates the points as much as possible with the largest margin. This is the problem that we have. We want to find the W, so we want to minimize a quadratic subject to a bunch of inequality constraints. So this is kind of the Lagrange multiplier problem, except that we have an inequality instead of inequality. But that's okay, because I think in the 50s, so I already covered this. Okay, now with inequalities. So this is the part that, this is where I'm going to start to kind of just give you the Coles notes or Eclipse notes. There's a version of Lagrange multipliers that handles inequality constraints. And so what ends up happening is if HI is your equality constraint, that's what we had on the example that we've just been working through, that gets a Lagrange multiplier. And then GI is an inequality, and that gets another Lagrange multiplier. So now, instead of having one set of Lagrange multipliers, which were called lambda before, because if you just have equalities, determine the standard is to use lambda. If you have both inequality constraints and equality constraints, the convention is to use alpha and beta. And so there's some tricks here, okay? So you want to minimize this, and you can't do what we did before. What we did before is to differentiate this with respect to W, differentiate with respect to beta, and solve. You can't do that anymore because of its inequality. And so that throws a wrench into that whole idea. However, there's a workaround, and I encourage, if this may not make sense to you live, but I encourage you to kind of stare at it at home to convince yourself that this is true. Consider this is called the primal optimization problem. What it says is, it's a new function, it's called theta p, and it's the value of the function is a maximum. Okay, so it's the value of theta p is the largest possible value of this Lagrangian that you can come up with, and where you're free to choose any alpha and beta, and alpha has to be positive, right? So and if you think about what that does, right? If you pick a W that doesn't satisfy your constraints, so let's look at H. If W satisfies your constraints, then this evaluates to 0. And no matter what value you choose for beta, this thing is going to stay to 0. However, if you pick a W that doesn't satisfy the constraint, then this just becomes some number. It could be positive, it could be negative. In either case, you can pick a beta that makes this go to infinity. And so the maximum of this Lagrangian becomes infinity everywhere except for the points that satisfy the constraints. And so what this method is trying to get at is it's trying to figure out a way for us to be able to easily evaluate what's a feasible point and what's not a feasible point. So you hear this term a lot. If you have a problem, it's just your contours. And let's say you have two inequality constraints. One is you have to be above here, and the other is you have to be below here. So your feasible region is all the points here that satisfy your constraint. And so what this is doing is it's saying, if I evaluate this function, I will know whether my point is feasible or not. And so the value of this function is finite only when W satisfies the constraints. So that's kind of step one. And then step two is that then that function, which is defined as a maximum over all possible Lagrange multipliers, I want to minimize it. So I want to find, right, and why is this a good idea? Because by doing this, I'm essentially solving that initial problem. And again, this is the part that I encourage you all to kind of stare at, maybe watch Andrew Ng's lecture, maybe now having two people explain it to you will make it easier to understand. Remember, you're trying to minimize this thing here. You're trying to minimize the max. And you should be able to convince yourself that by finding the W that minimizes the max, you are essentially solving this problem. You're solving this constraint optimization problem, because if you you will never come up with a W that doesn't satisfy the constraints. Why? Because then this thing, oh, that's cool. This thing will be infinite, and therefore it will never be a minimum. And that's kind of, again, that's like one of these mathematical tricks. And this is recent. This is like, recent. This is 20th century. Whereas Lagrange, I think, was like, I don't know, 18th, 19th century. And so now we can we can work with this formalism. However, that's not all. So that's step 2. And then step 3 is the real I guess breakthrough, for lack of a better word. It was determined that you can actually transpose this problem into what's called a dual form. So there's this duality. So there are many forms of duality in math. So for example, time and frequency domain is the one that everyone's familiar with. So you can look at a function in the time domain or the frequency domain. It's the same information, but it's just viewed in a different representation. So it's a very similar kind of idea here. And I think the way I'll say it, just I won't do it justice, but I think I'll get the point across, is that instead of doing min of a max, you can do max of a min. And the reason that this is an easier problem to solve than that, and what you can show basically that under certain conditions, the max of the min equals the min of the max. So basically, if you look at just the min term here, the min of W, this is saying for a fixed Lagrange multiplier alpha beta, I want to find the W that minimizes the Lagrangian. And then now that I have that, now that I have that evaluated for every possible alpha and beta, I want to find the alpha and beta to maximize that min. So it's the dual of the min of the max, which we agreed on was going to give us the solution that we want. And this is the key. The key result basically is that there is a really nice relationship between the function that you want to minimize, the f, and the max of the min. So theta d is the min, basically. So you're doing the max of the min here. And what that equation is showing, the one that's prefaced with "it can be shown that," is that if W satisfies your constraints, then the max of the min is finite. And if it doesn't, it's infinite, which means that we can solve our constraint minimization problem by working with theta d, the dual problem. And why is that important? Why? Because it's tractable to solve that problem. Basically, we're actually going to give you, I'm going to show you on the next couple slides what that looks like for support vector machines. We can't do that trick where with the simultaneous equations, but we can do this. So we have to derive a formula for theta d, and then we're gonna do a maximization over top of it. And then there's one, okay. So I just included this in the slide just to complete the the treatment of this constrained minimization. So we know that for just if for a one-dimensional, like a one-dimensional, not it doesn't have to be one-dimensional, but for a function that has no constraints and is convex, if the derivative of that function is 0, then you know you've hit a local minimum. For a function that has a constraint, you basically need the first 2 lines to be true. There's 5 equations here, unfortunately. So the first one is the standard one. You differentiate your function with respect to your independent variable, you set it to 0. So for W, I should back up and say these 5 equations, these are the conditions that if these 5 conditions are met, then you know you've solved your problem. This is kind of a sophisticated result. I don't expect you, this is not really, you know, I don't expect you guys to be able to derive these or anything like that. But the reason I bring them up is because this is the way that you test whether you've solved your constrained optimization problem. So if you have some routine, some function that gives you a guess of the optimal W, if you plug it, you know, you write your Lagrangian and then you plug in that value that your minimizer gave you. If all of these are true, then you know that you solved your problem as best as you can. And so some of these are trivial. This is trivial. This is just that the Lagrange multiplier on the inequality term has to be positive. And I'll explain why that's true. I mean, basically, the way that this is defined is our GIs are inequality constraint. So we have to be above or below a hyperplane. And the formalism is that whatever W we pick, it has to evaluate to a negative number. I don't know why they picked it to be a negative. They could have just as well picked it to be positive. But the idea is that for this Lagrangian to work, the multiplier on the inequality cannot invert G, right? So if you allowed alpha to have the opposite sign here as G, or like if you allowed alpha to be negative, then you'd be violating this constraint, which would obviously defeat the purpose of everything you're trying to do. And so the fifth line is really trivial. The one that's really, this is just saying that your W satisfies your inequality constraint. These first 2 are what we talked about last class, where this is your standard derivative of the cost function. This is the derivative of the cost function with respect to Lagrange multiplier. The third one is the interesting one, actually. And I'll just say it. What it basically says is that at your solution point, so remember GI is an inequality constraint. So GI means that you have to be above this hyperplane, right? And so let's say if you have G of W is equal to, if G of W is equal to W minus 1, then your inequality constraint is that W minus 1 is less than 0 or W is less than 1, right? So this is, you know, in this case, your inequality, this is 1, and so you have to be on this side of the inequality. Now, what's really interesting is that what this is telling you is that either your Lagrange multiplier is 0 or you are right on the boundary, right? Because one of these two, either the alpha I star is 0 or GI is 0. When GI is 0, it means that your solution is right on the edge of that inequality, which makes sense, right? Because like if you have a bowl, like if you're trying to minimize a bowl and you have to be on one side of the inequality, you're obviously, in many cases, you're going to be right on the edge. right? Because the edge, the edge is going to be the closest to the minimum of that bowl. But not always. So what's interesting is not for every constraint will you be on the edge, but for the constraint, because basically every eye here is a different constraint. That's kind of important. So you're either going to be on the edge of your inequality, or the alpha is going to be set to 0, which effectively means that that inequality is not being used. And so I think that what that means geometrically is that sometimes you have one inequality that by virtue of the others doesn't matter, because if you satisfy the others, you guarantee that you satisfy that one. I think that's not, I've never read that anywhere, but that's what my intuition is that if you have like redundancies, if you have something like, your solution, and I'm sorry for the people at home, maybe no, I won't switch because I'm about to go back, but if you have one inequality, you have to be below this line, and another inequality has to be below this line. Well, this one doesn't matter because, this one doesn't matter because if you're to the left of this line, you're already to the left of that line. And so I think that's what that equation is saying, is that your solution will not always be on the edge of your hyperplane, of your inequality. It's only the case for certain constraints. Yeah. Anyhow, I think if we have time at the end, I'll try to show you an example of F-min con with inequalities. Okay. But before that, I got to get to the end of this slide deck, which has a really cool result. Okay, so now the good news is now we're done with the theory of constraint minimization. And basically what happened in support vector machines, this is in the 90s. This is like, this is my heyday here. This is what's going on. This guy, I think the guy who came up with this worked at NEC Labs, which I think had headquarters in the great state of New Jersey. Big up New Jersey, Garden State, the state with highways and graveyards along the highway. I don't know why I felt like including that tidbit here. Vapnik is the guy who came up with Vladimir Vapnik. So he basically single-handedly invented support vector machines. And so what he figured out was that you can solve this maximum margin problem with this duality and Lagrange multiplier. So this is the thing that we want to minimize. And so this is maximizing the margin. And this constraint is basically saying that we need to get every example right. I'm not going to rehash this, but remember this is the margin. And so this is the Lagrange multiplier, and this is an inequality constraint. An inequality constraint. What it basically says is that every training example has to be on the correct side of the boundary. And so the insight is that the math is actually easy here, like the actual mechanics are not difficult. You can do this yourself. If you differentiate that Lagrangian with respect to W, B, and then with respect to just respect to the W, which is your hyperplane direction, and B, which is your offset, you get this really nice simple equations, right? And both these equations are going to have to set to 0, right? Which means that your W, and this is the insight, if you set this to 0, it means that W is equal to the sum of this. So I should put a box around this because this is like, this is both the equation that made support vector machines so popular, and at the same time, it's also kind of illustrates exactly why they don't work for a lot of these really high dimensional abstract problems like face recognition or natural language processing. So I'm going to try to explain that to you. So first of all, what is that equation saying? It's saying that your classifier is just a weighted combination of your input of your training data, right? So it's saying the W, that's your hyperplane, that's your decision boundary. So alpha is just a positive, not just a positive coefficient. Y is either +1 or -1. And so the important thing here is that W is a weighted summation of the X's. The X's are your training data. And so what it's saying is that your classifier is just formed from your training set, and this is saying that either the Lagrange multiplier is going to be 0, or your label is going to be 0. And what this essentially, I'll try to unpack this more on the next slide. What this is saying is that a lot of the alphas, a lot of the Lagrange multipliers are going to be set to 0. And the ones that are not set to 0 are called the support vectors. So here, I is a training example. Every training example gives you a constraint. So it's not a coincidence that you were using I's on the previous, the I on the previous slides was corresponding to the constraints, because every training example in support vector machines gives you a constraint. Remember, at the outset, we said, I want to get every example correct, and I want to get the maximum margin. So what this is saying is that we need to make this equal to 0. And one way to make that equal to 0, so Y, by the way, is either equal to +1 or -1, right? So if you have an equal number of +1s and -1s in your training set, then you can, even if you don't, you can always choose alphas. A set of alphas will make this 0. However, you can kind of intuit that some of the alphas will be chosen to be 0, which is very useful, because what it means is that the alphas that are set to 0 correspond to the training examples that you're not going to think are important. Okay, so this is the final problem, that is like when you run a fit SVM routine on on Python or MATLAB or whatever you use. This is the quadratic that it's solving. So it's actually working. And this is one thing that really confused me. I was like, where is the W? Like I thought we were looking for a W, and then I always saw the functions return alphas, and it's because of this duality. And once you have the alphas, you can get the W. Because of the equation on the previous slide that shows you that if you know the alpha, you know the W. And so what the support vector machine problem is doing is it's just solving another quadratic, but the quadratic is with respect to these Lagrange multipliers alpha. And if you do this, you will maximize the margin. Okay. This is the result that I wanted to get to. This is the equation that I was referring to, that is made SVM so popular, at the same time makes them less robust in some problems. So your prediction, so W transpose X plus B is your prediction. So X is a new data point. Xi are the training examples. So what this equation is saying, that when a new data point comes in, the prediction is going to be what's on the right-hand side. And what's on the right-hand side is that your new data point is getting inner producted with each training example. The value of that inner product gets weighted and then summed up across data. So in other words, what this is doing is it's essentially comparing your new data to your new data point to your training set, and it's figuring out which examples in the training set it looks most similar to. And when if I have And maybe now I'll switch to the board because I'm going to try to illustrate this with a picture. So my question to you guys is, stop share, right? That's what I need to do. Okay. So my question to you guys, so I have that equation I'm going to copy out here. I'll make this. So the prediction on X. So X is a new, X is a new date, new input. And Xi, Yi are, these are the training set. This is what you fit your model on. And what we saw was that the prediction was a summation across, I think it was alpha I, yi, and it was, and the way, one way of writing this, I like this notation a lot, is this means this is just an inner product. And for the standard, because there are different types of norms that are used. This is just a linear one where you have xi transpose x. So what does this mean? So these are all your training examples. And so first of all, this is alpha I. The first insight here is that if alpha I is equal to 0, then that example I in your data set does not matter, right? I wanted to draw a picture. The picture, I guess I'll draw it over here. I'll have two classes. And let's say that my maximum, my hyperplane is something like that. So and now a new data point comes in, and I'm going to draw, and I'm going to say this is my new data point. I don't have a label for it yet. And I need to figure out, which class do I want to put it in, the orange class or the green class? And now ignore the hyperplane for now. But what's basically going to happen with this equation is that certain, like this point here, will most certainly have a Lagrange multiplier of 0, and so will this one. Why? Because they're not important. They're not the examples that they're not the examples that the model has assigned non-zero alphas to, because what the maximum margin optimization is doing is it's trying to emphasize the examples that really drive where that hyperplane is. And so the examples that are going to be, so this example is going to be inner producted with everyone in the training set. And the prediction, if this inner product is large, then the weight of that example the training example, is going to propagate through to the prediction, which means that, let's say that, this is our training example, but this is our new data point. And let's say, actually, let's make this a bit easier for me to demonstrate. Let's say that I had a data point here. It was very close. Very close. And so the inner product between our test point and this training example is going to be very large, right? So this point here is going to have is an xi and it has a yi. And if yi is positive, then it's going to propagate through to the prediction. And so what I'm trying to say is that the training examples that have a large similarity, right? Because inner product is really a measure of similarity. Those are going to be the ones that are going to be weighted heavily in your prediction. And the way that so
it's not that the ones that are alpha 0 is because they're far away from the boundary, it's because they're far away from your data point, or is it?
It's a really good question. It's a really good question. So no, that'll be another. I don't know if I have time to show, but
We can circle back.
yeah, no, but it's a really good question. But it actually does work out that the ones. So basically, your support vectors. You're gonna have like a few support vectors that have non-zero alphas, and every example will essentially, every new example, whether it's here or here or here, will be compared to these three. So what SVMs are basically doing is they're picking a few really important training examples, and they're saying, compare it to this, and these are our three. These are the three examples that whichever one we're closest to, that's going to be our prediction. So it's essentially a template matcher, right? This is why shallow learning, which is what support vector machine is a template matcher. What you're doing is, if you want to discriminate between cat and dog in image space, you have some examples of a cat and some examples of a dog, and when a new image comes in, and you want to figure out whether it's a cat or a dog, you're basically doing a similarity measure between the thing that you're trying to predict and your training set, this is a wonderful kind of intuitive insight into what is happening, because this is all derived from just the mathematics of constraint minimization, but they got it to a point where they could actually see the template matching happen here. The problem is that, and this is why support vector machines kind of fell out of favor for these really complicated problems, is because there are limits to template matching, especially when it comes to things like images and speech. So I'll take the image example. I think it's the last thing I'll say today. So template matching is really, it's a nice intuitive thing. It may be, probably partly what the brain does is kind of like that. When people learn things, they may be, I'm sure there's some, when we have a representation of some object in our brain, when we need to perceive, when we look at something new, we probably are doing some kind of a perceptual template matching. But let's just say you have image one, let's just say this is, face one is good face recognition, face one and face two. The problem with template matching, and I'm not going to try to, so let's say the face one, face one, the eyes, are dead on, right? Maybe it's like that. Now the problem is at phase two, this guy may have a head tilt, right? and he may have a different look on his face. He may be bummed out that he's stuck in machine learning class. And so the problem is that these are both faces, but if you do an inner product in the pixel space between these two, it's probably not gonna, it's not gonna capture the similarity between the semantics of those two images. And that this is why, so support vector machines are great, but they're not great if you have a lot of, so the term that is used here, you want invariant representations. So this is an example of not an invariant representation. Pixels of an image are not invariant to the object, right? Because you can capture the same object and it can look completely different in pixel space. And so kind of the thing about, and I'm trying to get to deep learning as fast as I can in this course. The thing about what deep learning has really done is it still does template matching in a sense, but it doesn't do it on pixels. It does it, I have a minute. So basically what deep learning, if your pixels are at the bottom, and then your next layer up, and then your next layer up, etc. So these are your pixels here. And then this next hidden layer may capture edges, maybe, right? So it will capture, like, it looks for certain combinations of intensities. And then this thing the next layer up will capture contours. And then the next layer up may capture, whatever faces or something. And so and what it does is it does do a template matching up as you go up this network. It's not doing it. It's called shallow learning because everything is happening at this level. Whereas what you really want to do, is you want to do the similarity matching at that level. You want to look for contours. And by the way, the reason, this is one thing that it took me a long time to figure this out. The reason why we need all these different units, and again, this is not never see this in the textbook, but I think that the reason you need to have these very wide layers in deep learning is because the contours can appear with different orientations in different parts of the image. And so, like, maybe this node will represent a face in the top left. This one will represent a face in the top right, and they're all important if you're doing face identification. But you need to be able to it's not just the contours of the face. You can have contours of a face appearing with different orientations, different lightings, and also in different parts of the image. And so if you look at a neural net kind of diagram, you'll see that there'll be many, many, many nodes. It'll be like 1,000 nodes maybe in a layer. And the reason you need all 1,000 is because you need to account for the different image positions, for example. Okay, right on cue. Bye-bye, YouTube and virtual viewers.